This lesson is on inverses and one-to-one functions, and this time we're going to do a little bit more algebra with inverses. So let's remind ourselves what a one-to-one function is. A one-to-one function. A function with a domain A is called a one-to-one function if no two elements of A have the same image or element in the range. Basically, the x's have to be different to make it a function. And the y's have to be different to make it a one-to-one function. So this is a mapping showing you that this function is one-to-one. We have a 4, 3, 2, 1. These are elements in the input, and they are mapped to unique elements in the output. So this is a one-to-one function. This mapping, the elements here, 4, 3, 2, 1, are mapped to elements in the output, but 3 and 2 are mapped to the same output. So that's not one-to-one. You may remember from Unit 1, we used the horizontal line test to test whether a graph is one-to-one or not. So this one looks like half a parabola, and it passes the horizontal line test. So this is one-to-one. Therefore, it has an inverse. So that's why we learned about one-to-one functions, because only one-to-one functions have an inverse. Okay, this quadratic right here fails the horizontal line test. So it's a function, but it's not one-to-one. So as it stands, it does not have an inverse. But this is a huge concept. We like to talk about quadratics a lot. So we can easily make this quadratic here one-to-one if we restrict its domain. If I say this quadratic, by the way, is the equation f of x equals x squared. Okay, right now it's not one-to-one. But if I just say, hey, just look at this part of it, just this branch. If I restrict the domain, if I say, okay, let's just make the domain from 0 to infinity, then now it is one-to-one and it has an inverse. Okay? All right, first algebraic lesson here with inverses. Showing a function is one-to-one. So to show a function is one-to-one, we have to show that if the outputs f of x1 equals f of x2 are equal to each other, so if the outputs equal, or the range values equal, then that means that the inputs must equal. That would mean we're making sure that each x and y is paired with a unique number. Okay, so let's show how to show that a function is one-to-one. Okay, so what we're going to do is we're going to start right here. We're going to say, well, let's let f of x1 be 2 over x1 minus 3. And let's let f of x2 be 2 over x2 minus 3. Well, we want them to equal each other, the if part. So we're going to set these equal to each other. 2 over x1 minus 3 equals 2 over x2 minus 3. And now we're going to do a little bit of algebra. We haven't talked about cross multiplication yet. Cross multiplication is a big deal. It's a great tool. If you have two fractions equal to each other, you can cross multiply. So what you do is you take this denominator here and multiply it to the numerator over here, and that's going to give you 2 times x2 minus 3. equals, and then you take this denominator over here and multiply it to that numerator over there, and you get 2 times x1 minus 3. It's called cross multiplication. It gets rid of the two fractions. Alright, now let's distribute. So we get 2x2 minus 6 equals 2x1 minus 6. Alright, the minus 6 on opposite sides, they cancel each other out. So that's 2x2 equals 2x1. Divide both sides by 2, and you get this conclusion. So we said that if the outputs are equal to each other, then the inputs should be equal to each other. And they are. So we just proved that that function is one-to-one. To prove that a function is not one-to-one, it's a lot easier. All you have to do is find a counterexample. So just find a pair of x values that don't equal each other, and yet they give you the same range. So let's look at B here. Determine if the function g of x equals x squared minus 2 is a one-to-one. Now I happen to know what this is. Do you know what this graph is? It has an x squared in it. This is a quadratic. Do you remember what the minus 2 does to it? Just to review, moves it down 2. So this is a quadratic down 2. So if you can solve it this way and say, well, I know what the graph of this looks like and it fails the horizontal line test, that is a fine way to determine if the function g of x equals x squared minus 2, at least in my class. But if you wanted to show it was algebraic, show the algebraic method, what we have to do, it has to do with this x squared. See, when you square a negative number, it turns positive. So what I'm going to do is I'm going to let one of the x's be 2, and I'm going to let the other x be negative 2. Okay, two different x's, right? So if we plug this in, g of negative 2 is equal to negative 2 squared minus 2, which is 4 minus 2 is 2. So you get the ordered pair negative 2, 2. And if we evaluate g of 2, we get 2 squared minus 2, which is also 4 minus 2 is 2. You get 2, 2. And so we have shown that when you choose two different x coordinates, you get the same y coordinate or output. You choose different inputs, gives you the same output. Therefore, it is not one-to-one. That's how you would show it algebraically. But that's like over here on this graph saying, all right, negative 2, 2 is on the graph, and so is 2, 2. It fails the horizontal line test. Next. Determine whether each of these functions is one-to-one. Okay, well, I've shown you how to do this. So what you would do is you would say 3/4 x1 minus 1/2 equals 3/4 x2 minus 1/2. Well, the 1/2s cancel, and then 3/4 x1 equals 3/4 x2. Divide out the 3/4. They divide out to 1, therefore x1 equals x2, therefore it's one-to-one. But I'm just showing you the work, but I knew that because this is a line, right? And a line with a positive slope and a negative y-intercept is going to pass the horizontal line test. Okay, example B, a little bit harder, and a lot harder actually if you do it without a graph. But if you think about it, you know this is a quadratic. So it's a U-shaped graph, so it's not one-to-one. The reason it's a lot harder is because I can't just pick like 2 and negative 2. I can't just pick opposites, because the square, that would work well, but there's a x that's not squared, and so it's going to make it harder to find. So I had to think a little bit about it, but I'm going to let x equal negative 1, and that would give me 6 if I plug negative 1 in here and here. So to find another x coordinate that has that same output, I actually have to set this equal to 6, and I can find it. Now I had to go off camera and test this because I don't want us to have to do the quadratic formula, but I do want to review how you solve a quadratic equation, so this is helpful to review. Alright, so here's a quadratic equation. Do you remember how to solve it? Well, remember you have to set it equal to 0, so I need to subtract 6 from both sides. So that's 2x squared minus 3x minus 5 equals 0. Then I have to factor it. So if this factors, it's going to factor into two binomials, and it does. I checked it off camera. So remember, the factors of 2 are 2 and 1. So we know this will be a 2x and that'll be an x. The factor of 5 are 1 and 5, and that's it. So because this is a 2 and a 1, I have to check the outer and inner terms. And I have to put 1 and 5 and just test them out. Okay, so I'm going to do it wrong first so you can remember how to do this. So I'm going to put a 1 there and a 5 there. And now I'm going to use this minus. The outer and the inner terms have to subtract to be 3. So the outer term, that's 10x. See that? This is 1x. 10 minus 1 is not 3. So it's not 1 here and 5 there. Let's try 5 here and 1 there. So then the outer terms, 2x times 1, that's 2x. And the inner term is 5x. Do they subtract to be 3? Yes. So then the last thing I do is I want it to be a negative 3. I know I've got the right numbers, but I want the 5 to be negative and the 2 to be positive. That's how they will subtract to be a negative 3. So I know I need a minus here and a plus here. Okay, so after you factor, you set each of these factors equal to 0. And you get x is negative 1, which we already knew. And then over here you get 2x equals 5 and x is 5/2. So that's our second x. So that's quite much a big jump to find without using the graph to show that it's not 1-to-1. But I did. I found two different x values that gave me the same y value. Right? We now know that the order pair -1, 6 is on the graph, and the order pair 5/2, 6 is on the graph. And so it's not 1-to-1. Okay, probably won't have one that difficult to do. I hope you are saying to yourself, I wish I could I understand the graph part. I know that's a quadratic. I know that fails the horizontal line test. If that's what you're thinking, that's really good. But solving this quadratic is very helpful to review. And we'll just move on from these. I think I've done enough of those. So let's see what else we have here. Now, we've been talking about 1-to-1 functions a lot, but the big deal about 1-to-1 functions is that they have inverses. So the reminder about what an inverse is, if the function's 1-to-1 and you have a domain A and a range B, then the inverse function, and that's the notation, has domain B and range A. So the domain and range is switches, and it's defined by this. If you have f of x, the input is x and you get output y, well, the inverse function, if you put that output becomes the input in, and you get x, the input there. So the output and the inputs switch. Okay. Remember the notation, f to the -1, it doesn't mean 1 over f, it just means it's the inverse of f. There are 3 properties that you want to remember, and this is review. When I first told you this, we didn't understand function composition, but now we do, so let's look at it. So if f is a 1-to-1 function with domain A and range B, the inverse function satisfies the following cancellation properties. If I put the original function into the inverse function, it's going to come out to be x for every x in A. And if I put the inverse function into the f function, it's going to equal x for every x in B. So function composition, It's saying that if I compose f with the inverse, I get x. If I compose the inverse with f, I get x. The second property is that the inverses, the graphs of the inverses, are symmetrical about the line y equals x. And the third property is if you have a point AB on the function f, then the point BA will be on the function, the inverse function. And remember, the line y equals x, if you draw a perpendicular line, you'll find those values. So you can just switch the ordered pairs. You can switch all the ordered pairs. So again, the domain and range are going to switch. So that's another property as well. Okay, so that's review. But now for the new thing. How do we algebraically find the inverse of a one-to-one function? Well, the steps are listed there. And so I'm just going to go through the first one with you. We have a linear function. Okay, that's going to form a line. Y equals mx plus b. Slope is negative 5. Y-intercept is 3. So it has an inverse because it's one-to-one. So step one, what you're going to do is just replace this f of x with y. We like to do that anyway, right? Okay, and then step two is we're going to, this is using the property of inverses, we're going to switch the x and the y, because that's what all the ordered pairs do. And then step three is we're going to solve the equation for y. So this is where the algebra happens. Okay, so we've got this y and we want to get it by itself. It's being multiplied by negative 5 and 3 is being added. So we have to undo what's being done to y in the opposite order. So we wouldn't want to get rid of the multiplication first, we want to get rid of this 3 first, and we wouldn't want to subtract the 3 because it's technically not being subtracted. This is a positive 3, so we're going to add a negative 3. Okay, not because of that minus, but because the opposite of 3 is negative 3. And those aren't like terms, so that's just x minus 3 equals negative 5y. Then we're going to divide. To the undo multiplication, we divide by negative 5. And that gives us y equals, you can give this negative to the top if you want. If you multiply everybody by negative 1, you get a negative x plus 3 over 5. Okay, so that's step 3. We solved for y. Step 4, you just replace this y. You want the right notation. So the inverse function f is equal to negative x plus 3 over 5. Some people like to distribute that 5. You don't have to, but if you did, that would be negative 1/5 x. If you see right there, negative x over 5 is negative 1/5 x plus 3/5. Okay, so those are your steps. That's how you find the inverse. Okay, so we can look in the lab manual, see if you can find a line to try. Alright, the second one is very tricky because this function is a rational function and it has an x in both the numerator and the denominator. Okay, it also has a domain restriction. Alright, remember you can't have 0 in the bottom of a denominator, so remember the domain, x cannot be 2. So if I set that not equal to 0, x cannot be 2. Okay? Alright, so now how do we find the inverse? Well, step 1, we replace this f of x with y. So we have y equals 3x over x minus 2. Then step 2, we switch the x's and y's, so this would be x equals 3y over y minus 2. Okay, so now we run into a problem. We want to solve for y. We want to get y by itself, but y is in the numerator and the denominator. And this is a grouping symbol. Okay, so you have to know how to do this, and I'll write down the steps. They aren't going to change every time this happens. You have two y's, you can do this. So I remember in the last lesson I talked to you about cross multiplying. Cross multiplying is what you're going to do here because you have a fraction here, and you can make x a fraction by putting it over 1. So we're going to cross multiply, and that's going to give me x times y minus 2 in parentheses equals 3y. Okay, now if I distribute that x, I get xy minus 2x equals 3y. Okay, now here's another new, very, very important concept. How many terms do you see? Do you see 3 terms? You have to start being able to see terms. And do you see how this term has a y in it and this term has a y in it? And remember, your objective is to get y by itself. So what we want to do is get our y terms together and get our non-y terms over on the other side. And I can move terms over the equal sign without having to do a bunch of whatever I do to one side, I do the other. There's a new concept you need to kind of get used to, and that is you can move things over the equal sign as long as you change their sign. So if I don't want to move the xy, I'm going to leave the xy. Okay, it stayed on the left, so it doesn't change. But if I wanted to move the 3y to the left, it's going to become minus 3y. Alright, and if I want to move the negative 2x to the right, it becomes positive 2x. Okay, so 3 terms, I got the y terms on the left and the x term on the right. But anytime I move something over the equal sign, I have to change its sign. But now what I've got here is I've got xy minus 3y. And again, in the difference quotient lesson, I talked to you about how nice it is to factor out GCF. So these both have a y in common. So the next step is I'm going to factor out the y, and that'll be leave me with x minus 3. So y times x minus 3 is the same as xy minus 3y equals 2x. And then, so the last step, I can divide by this one thing, x minus 3. That's one thing. So that's legal. And so y equals that. Well, I'm going to change the notation to inverse of x equals 2x minus 3. And that's that. So this is always tricky for students, but the same steps happen every time. Not only these same steps, but these same steps. So we cross multiplied. We distributed. We moved terms, y terms, together. We did that there. Okay, and then we factored. And then we divided. Okay, so those steps are always going to be what you do when you are asked to find the inverse of a rational function. Now, back to domain. Remember, the domain of this inverse, of this function, was x cannot be 2. Well, what's the domain of its inverse? That domain is x cannot be 3. Well, here is a great use of this property right here. The domain and the range switch places. Okay, so I would not want to have to try to find the range of this function, because I'd have to plug the 2 in, have to kind of figure out, I can't plug the 2 in because I get a 0. It's really hard. But the cool thing is, if I know this domain, which was easy to see, of this inverse was not x not equal to 3, then that means that the range of the original must be x not equal to 3. And if this domain of the original function is x can't be 2, then that must mean that the range of that inverse is x can't be 2. So that's kind of helpful, is you can find the domain of each of them and then use that to find the range of each of them as well. Okay, if I were in class, I would give us another one of those to try, so I'm going to do that here. So let's say, excuse my cat, I have f of x equals 5x over 2x plus 6. Okay, stop the video and try to find the inverse of this, and you can look at your notes for how we did the other one. Okay, I'm going to do it now after you've had a chance. So what we're going to do, switch the x's and y's. So this is going to be x equals 5y over 2y plus 6. We're going to cross multiply. So that's 2xy plus 6x equals 5y. I'm skipping a few steps. What I did was cross multiply and I went ahead and distributed. Okay, so I have three terms. Did you get three terms? So I want to get my y's on one side. So 2xy minus 5y equals negative 6x. So I had to move this to the left and that to the right. And now I'm going to factor out the y. And I'm going to divide by that 2x minus 5 expression. And so y, which is inverse of f, is equal to negative 6x over 2x minus 5. By the way, if you move the y's, this y term over there, you might have an answer as 6x over 5 minus 2x. Those are equivalent. Those are opposites. See how all of these are opposite signs? That's the same thing. Okay, let's just look at the domain really quick. What would be the domain and range of the function? Well, this cannot equal 0, so if we set that not equal to 0, x cannot be negative 3. Well, I don't want to find the range, but I can be smart and go find the domain here. 5 minus 2x cannot be 0. Negative 2x cannot be negative 5. Divide by negative 2, and x cannot be 5 halves. Okay, so that's the domain of the inverse, which means that's the range and this is the range. And I should change this to y. I just realized that because we're talking about outputs. So I'll go fix that over here. It should be y. There, I didn't put it in inverse notation, which I'm used to doing, so that's why I made that mistake. You would have to put it in interval notation. All right, so hope you did well with that one. All right, let's look at a different type. Do you know what type of function this is? This is a radical function. It's going to look something like that. Okay, and so to find the inverse, the steps aren't going to change. So let's see what happens. So this is y equals the square root of 2 plus 5x. This is x equals the square root of 2 plus 5y. Okay, so now some new algebra. You can square both sides to get rid of that radical. So that's x squared equals 2 plus 5y. Alright, so to get y by itself, we're going to subtract 2. So that's x squared minus 2 equals 5y. Okay, to get rid of that 5, I'm going to multiply by 1/5 both sides. So the inverse function is 1/5 times x squared minus 2. Or 1/5 x squared minus 2/5. Either one. But that's a problem. Okay? This is a quadratic and it looks like this. And that's not, does not pass the horizontal line test, so this is not 1-to-1. So you have to play around with it a little bit. You have to restrict the domain of this inverse. Okay, well, let's go back and look at the domain of this radical. Do you remember how to find the domain of a radical function? Right, you have to set what's under the radical cannot be negative, so you set it greater than or equal to 0. So that means that it's going to be x has to be greater than or equal to negative 2/5. Okay, well, I know that it looks this way. It's an increasing function, so to find this range isn't too tough. I'll actually use interval notation this time. to find the range, all you have to do is plug in this smallest value here. So if I plug in 2 plus 5 times negative 2/5 to find out what the y is, the y coordinate partner for that, that's going to be 2 plus a negative 2, and you get 0. So you end up with a range. So what's happening is you have a domain of negative 2 to infinity, but you have a range from 0 to infinity. Okay. So now what we can do is use this info to restrict this domain so that it is 1 to 1. And basically I just want to get rid of this left branch. Okay, so you can see that the range of this function here is going to be the domain of the inverse. So what we're saying is that this does have an inverse as long as I restrict the domain to 0 to infinity. That's a tough critical thinking question. I know that just blew some people's mind, but you need to study it because it's something that we focus on. If you like to memorize things, radical functions, the inverse of a radical function is a quadratic with restricted domain. Okay, so if I wanted to graph this, remember inverses are symmetrical about the line y equals x, and if I wanted to graph this, the inverse should make sense. It's going to be a half of a parabola with domain from 0 to infinity. So you have to restrict the domain of this inverse once you find it. Okay, so this leads me to a common WebAssign question. It says find the entire domain on which the function f is 1 to 1 and not decreasing. Okay, that's interesting. Write the domain in interval notation. Then find the inverse of f restricted to that domain. So this is the opposite of this question. I've given you a quadratic, and let's draw that. Now you should be able to draw it. Do you know what a quadratic looks like? Looks like a U, right? Do you know what that plus 8 does inside with the x? Yep, moves it left 8. So this is the graph of that. So we can use the graph to unpack this. Find the entire domain on which this function is 1 to 1. Is this function 1 to 1? No. So we need to erase part of it. Well, which part? Find the entire domain on which the function is 1 to 1 and not decreasing. So which part of these branches is not decreasing? This part's going down as you go left to right. So this part's decreasing. So this is the part that is not decreasing. And that domain is bracket negative 8 to infinity. Okay, so this question, I love it because it asks you to have a lot of knowledge about different things. Translations, what does a quadratic look like? How do you restrict the domain? So we have the domain now, and then it says find the inverse. See, before it wasn't 1 to 1, but now that we've restricted the domain, it is 1 to 1. So now we can do the algebra part. How do you find the inverse? Well, you switch the x's and y's, and you solve for y. So to get rid of a square, you're going to take the square root. And that square root and that square cancel. Now, normally when you take the square, I would say it's plus or minus x, but because we've restricted the domain, we're just going to say it's x. So now if we subtract 8, we get, I lost something. I lost my square root. Okay, square root of x. You're not going to put a plus or minus in front of it. Okay, so now subtract 8 and you get square root of x minus 8 equals y. So the inverse is this radical function right here that looks like a radical function but shifted down 8. And they do look like they are symmetrical. Okay, so this domain, x has to be greater than or equal to 0, is 0 to infinity. This range, we already know it because it's the same as that domain. Okay, so that's a great WebAssign question where you have to have a lot of knowledge. And that's it for inverses. There's some to practice in the lab manual.